Good morning, everybody. Today's lecture is about dynamic experiments, and I think many of you have this kind of experiments that you want to follow something happening over time. And I will show you a couple of things that are interesting in this context today. First I need to get that one working. So the literature, the always returning John Ross tells us always something good. A new book, if you're interested into this topic, I would recommend the book Image Registration Principles by Ardeshir Ghoshtabi. I think that is probably the book that covers most methods in the topic of image registration. You can download it from Springer Link, and you get the link down here. So I think if you're interested in registration, here we'll probably have the theories that you need. Then, of course, there's a couple of papers that are related to this lecture. So if you want, you can also take a look at those. And well, just as a recap of what we have done until now, we did image enhancement, getting rid of the noise, maybe enhancing some image features. Then we went over to histograms and ways to segment the images and also label them. And once we had the labels, we started doing analysis on these labeled items. Then, as last week, we started looking at also the shapes more in terms of skeletons, and also looking at touching items using the watershed segmentation. So we have a pretty big toolbox already to work with. So now in this class we have, it actually has the name quantitative big imaging. So now is the question, what is big? Until now we haven't been talking really about what is big. Big data is a kind of a topic that you probably have heard about a lot. It's fancy to talk about big data things, but what is it now with imaging? We have talked about imaging, of course. We have been talking about quantitative, but now is the question, what is big? So it's not just or even large, it's really huge. In some cases, we are talking about several terabytes of data that needs to be processed. A single picture is some few megabytes. So you can imagine what terabytes of data would mean. What does it really mean now that we want to be ready for big data? So the first thing we want to look at, what actually expands the data, are the 3 V's. Volume, starting doing tomography, velocity, things that are moving, and in many cases you also want to talk about variety, because a single sample is just a single observation and you can't do any statistics about it. So you need several replications of the same sample or the same behavior in order to do any decent scientific analysis of the data. What we need is something that is scalable, fast, and also easily customizable, so you can adapt it to what you are doing. Not that it's really strict, fixed on a specific task that you have right now in front of you, but also that you can modify it easily in a way that you can use it, or maybe even your colleague can use it in a next experiment. So now we need to do analysis in very disciplined manner. So we need some fixed steps. It should be easy to regenerate the results in each step. And of course, magic parameters, they are banned in this concept. Because if you start adding magic parameters to each step, you have to tweak and tune every time you change the data. And that's not really reliable. We also need to have it automated or easily automated. So if it works on one sample, you should make sure that it also can work for the next 100. And of course, it will take more computational time, but that's part of it. But that's only the computer working. The idea is you should try to design your analysis workflow in a way that you only give it a list and then it does something about that list. And in the end, you get a beautiful graph that you have in your next award-winning publication. So what we need is a bunch of well-working scripts and easy way to modify the parameters. So that could be that you want to work on different types of cells and you have to be able to modify a little bit or maybe work on different regions, maybe adaptive regions. So the script is actually taking care of finding which regions you should look at. So there is a lot of things that you need to put into the thought when you plan the analysis. And actually all that thinking actually already starts at the experiment or when you prepare the experiment, that you think already from the beginning, how am I going to analyze this data? That's very important to think about that from the beginning, because otherwise you will end up with a big pile of hard drives and you don't know where to start. So it's important to plan the whole sequence, not only as being happy running to the beamline like the one I have behind me right now. That will not work when you start analyzing the data, and that's usually the largest lag in a scientific project is missing strategies for an analysis, because that is where the major time is spent. So we need some objectives to work with. So first of all, what kind of dynamic experiments are we talking about? And also, how can we design good dynamic experiments? It involves exactly this planning. And then afterwards, in the image analysis, what is it we want to analyze? Not just strolling around in the forest of methods, but really having a good plan. What is it I need to answer the questions about the samples I want to have? Sometimes, of course, in the beginning, you need to get acquainted with data, of course, a little bit playing in the beginning, but afterwards we have to go pretty straight on to what we are doing. So can we track objects between different points? Can we track the shape changes? Can we track distribution of different families of items, for example, or the topology? And also, how can we follow different voxels? But actually, that is going down to a little more technical detail. Also, how can we see if there is a deformation or strain in the sample? So, and of course, in the end, how can we put this together into a more generalized framework? And now is a question how all these questions are going to answer your questions, and that's a question for you actually. Now that you have a big toolbox, you have to put it together and make some smart thinking to bridge the methods to the questions you want to have, you want to answer. So that is actually your task. In some cases, if you want, I can help you. And also, if you now are going to do a project, some have approached me with some ideas. If some of you would like to have a suggestion, I still have a few on stock, which are not written on the list. But anyway, if you want to kind of do some sparring with your new methods, that is the chance to do it under mine and No, come on. Lost his name. It's too much. No, I'm lost this morning. Sorry for my poor assistant. Anyway, so let's go on to the outline. So we have a little bit motivation, some scientific goals. Then we do some experiments and experiment design. And then we go over to object tracking and topology. And first, we want to look at different methods that we could work with. So the pixel and voxel-based methods. Cross-correlation is one, looking at the correlation between different images. And actually, DIC is an abbreviation of digital image correlation, which is a method where you can track movements within images. That, of course, you can connect with physics, and then we can look at different transforms of the objects. Another way of looking at how things are moving around is, there's one question. Let's look at it. Stefana, very much thank you. I'm lost this morning. I don't know what happened. Yeah. So the other thing is looking at key points. That is a actually some slides that are extracted from this main lecture notebook. And then we can look at some general problems, looking at real applications and see what we can get out of that. So let's look at some data, and here is a little example of tomography data set in time. So it's a foam that is bubbling, and we want to analyze how that is working. And as you can see, it is not easy to think and work. So already thinking and working in 3D already requires some work, as you may have noticed already, but expanding it even further to fourth dimension, that is even harder, and you have to have good strategies to work in that. But also, as you can imagine, already in 2D, we have some problems when you go out in time. So actually a movie can also be observed as a three-dimensional image. So we have this example. You see the movie of a water jet with some bubbles in it or some particles that are flowing through. As I remember this experiment, it was a pretty fast acquisition. So it was done at Tomcat beamline, and it was extremely rapid acquisition in this case. And you can see it's noisy, so it's on the limit on what can be done at the beamline. Another experiment, which was, I would say, a fun experiment, something I did to test a camera. So we put this Italian coffee device and started making coffee in the beamline. So the beamline smelled beautiful. It was a lovely smell in the beamline, but working in control zone, we were not allowed to drink the coffee. But anyway, it smelled good. And what you can see here is a three-dimensional visualization where you can see that in the beginning, there is a lot of water in the lower compartment. And then when it starts boiling, you can see a little bit ripple. That's probably bubbles. And then the water is disappearing from the lower compartment and going through the coffee. And then after a little while, you can see that it's sprinkling out. You can see the sprinkle on the rooftop. And then you see that the coffee is getting ready in the upper part. So this is a way of visualizing time series, which I've been using a couple of times. Sometimes it's easy to explain what you're doing, and sometimes you can even use this kind of visualization to observe physical phenomena. I used it once in a student project to look at the capillary rise. in a porous medium, and you could very beautifully see, you could extract the trend line of the waterfront in the porous medium and nicely fit it to square root of time, which is the model that is used for capillary rise. If you want to see the movie, you can also click on this link. It's a YouTube movie, and it actually made me a YouTuber in a kind of way. I think I have about 60, 70 clicks, 70,000 clicks. So it's not too bad. Anyway, all about that. So when you're starting having this time series, you have to start asking again your questions. What information is it you want to extract? So, for example, how fast is something happening? How many particles are present at a certain moment in time? Does the size change, or is it constant, or is something moving around or accelerating throughout the experiment? And also, is there some kind of rearrangement? For example, if you have a sedimentation process, you can see that in the beginning, it's very compact, very spread out. And then when it's sedimenting, you can see that it's getting more and more compact over time. So things like that, or if you have even also with the sedimentation, you can maybe even extract some particle size in this sedimentation process. So things like that you would like to observe and put some numbers on. Other thing is, of course, we can have 3D reconstruction, so the tomography case. And that is probably most of you know about computer tomography methods to acquire a lot of 2D projections and from different directions, and then you can reconstruct it into a volume image. And that's the usual way that we at PSI are producing our three-dimensional images is computer tomography. And then we repeat that many times to get the volume time series. Another way is in microscopy, where you can't rotate the whole sample all the way. Then instead, what you do is you tilt the sample or rotate it a little bit to get some few extra angles. And with that, you can get some depth information in the sample. So that's an alternative way, actually algorithmically related to computer tomography, but it's more underdetermined than that case. So now we have talked about parameters that you can investigate, but now you want to understand something also. So that would be how liquids are mixed or are mixing, for example. So blood movement in arteries and veins and capillaries, oil movement in porous rock, or even what's happening in the dough when you're baking bread, or to go a little bit more extreme, magma and gas distribution within a volcano. Other things would be deformation. So how are the blood cells deformed? Could also look at microfractures in stretch fractures in bone, or a project that I'm involved in is looking at the self-healing properties of asphalt. So, and then also seeing what's happening in different wood types when they are loaded, or in some way compression, pulling, or something like that. So for the experiment side, we have a lot of limitations, technical limitations, physical limitations. So the first one is we don't have infinite detectors. So we have to limit the field of view into something, because otherwise we wouldn't be able to capture the information. Then the next thing is the voxel size, also the rate of the measurements, how fast can we measure? We have dose limitations. So we can either on one side have sample damage. If you push too much energy into the sample, it somehow will be damaged. The other side of the dose is that we have limited flux, and that gives us possibly too low signal to noise ratio. And there is always some damage in the experiment, so we have to balance in that too. And that is what we have to put together in a big bowl and in our experiment planning. So this can be put together or visualized in this triangle graph that I made. You have the feature sizes that you want to look at versus the resolution. Or you want to looking at individual features or more the bulk properties. The process speed versus the frame rate. So it's a sampling thing again, but in time. You need several points in time in order to be able to follow the process. But well, if the flux doesn't allow it, then of course you have to settle possibly with something else. But then you could come to the position that it's a step function, that nothing, everything. The other one is the signal to noise ratio. You also want to push, but all these together, they pull in some way around so you have a limited number of neutrons or photons in the experiment, and you have to make a budget of how to work with those. So one way is to tune the experiment by simulation. So you can have, one is doing Monte Carlo simulations, checking what is the experimental acquisition properties, and the other side is looking at the process, doing some simulations in advance, checking how far a process will go, how long time it will take, how rapid transients are, etc. So there is usually a way to work with simulation to get this. But in other cases, you are unfortunate and you inherited a bunch of hard drives with data, and now it's your task to do something about it. Then you can't do much about experiment design. So that's a pity for the one who has to do it like this. But anyway, sometimes you can plan and do it thoroughly, because you will thank yourself afterwards when you start analyzing the data. So what do we start with when you start doing our analysis? So let's go back. Actually, now I'm going to show a little bit example of how to track information. And first of all, go back to the cell image we have been following throughout our lectures. So in the beginning, we want to get rid of noise, find where the cells are. Then we want to analyze the shape. We can use the shape tensor, how to see how the shape of the cells vary. We want to separate cells that are joined. That can be done using the watershed segmentation. And we can even have some metrics to characterize distributions in the images. But anyway, we now have some data, and now we want to do something with it. And first, let's start with a basic example, just a lot of dots on a plane like this. And from now on, there is a lot of code, Python code written, and I tried to hide some of it. In some cases, I actually kept it, but anyway, the important thing is the message about what you see in the images. Of course, it's beneficial if you also look at the details in the code, but that's not the part of this lecture that you should understand the code as I'm talking right now, because that would be really too intense. So let's start with this image. We have some dots. So in a map of zeros, we have some dots that are equal to 1. And when we look at them, we can start moving them. They are really a marching army. In this case, I don't think any cells would move like this. But anyway, they are moving now pretty linearly in a nice cluster. So let's look at what they're doing. The first thing we need to do is, of course, thresholding. We need to do component labeling, so we know which cell is which. We could do shape analysis and distribution analysis, but in this case, it's not really needed. But we get all this information and put it in a data frame. And actually, I don't think I mentioned the topic data frames, but I've been using them pretty much. Anyway, so the question is, in the future, would you like to have kind of an introduction to what data frames are? Because they are very useful tools, and when you do this analysis. So I could imagine making some side short introduction to data frames, if you would like to. You can give me a thumbs up, or if you would like to have something like this. And it seems like it's liked, so I'll try to put something together. I can't tell when, but I believe we have some time in May where I could put together something like this. Another thing that I've been thinking about is we have been using Git. For some of you, maybe it was a little bit intense. So that could be like a technical lecture where I show data frames and how to work with Git, or how I am working with Git in my projects. So that is really a pure technical lecture, so it doesn't have to really to do with the main topic of this class. But anyway, I could do it if you like. So as I think people want it, so I try to put something together about mid-May or something. Anyway, now we got a little table here. We have, well, this particular table doesn't show much. So we measured some information like the centroid, the area, and the frame index, and the label. And all that is put together in a data frame, which is kind of a database or just a table actually, but you can do a lot of fun stuff with it. For now, we just look at and see we have different labels, we have positions, and the area is 1. As you could see before, it was just a single pixel. And the frame index in this, what we see is just the same. So everything is from the same frame. So now look at the positions. We have now in this picture, we have put all frames in one image. So now we can see we have frame 0 is red, frame 2 is, frame 1 is blue, purple, gray, and yellow, etc. So we can see that we have a time sequence in this data. With this, we still don't know, or we don't show which label each item has, because that would look differently. And now we want to describe the motion. And in this particular example, we actually have a velocity moving -1, -1 in this example that I showed. So it's not very fancy, but it could look something completely different. So we need some kind of scores to see how well we can find the tracks, and there are also a lot of information in the papers in the initial part of the lecture. And these metrics we are looking at right now is sometimes very easy, and there is a lot of complicated approaches. Some are extremely complicated, even based on the physics of what you expect, etc. But in the beginning, it's often best to start with a very simple approach that is easy to understand. And in our case, we will start with the nearest neighbor and looking what that looks like. And of course, you could add multi-hypothesis testing, neural network models. But if you need to work with that, you have to rethink what you're doing, and maybe it's not so reliable. Maybe it's just a special case that works with it. So you have to be careful. The more complicated tracking methods you need to take, the more critical you have to be to what you're doing. So what we do now is to look at nearest neighbor. Very simple. In principle, we have done it already in other contexts. So we have a point in image 0 at time point 0. And we want to match it to a point in the next image. So what we are doing is to look at the point that we are having right now, and looking at the different positions, point positions in the data, and see which one is closest to the one in the first image. And from that, we get something like this. So we can see that this black dot is relatively close to those two, and much further. So actually the alpha coding here is that it's more transparent the further away we are. And from that we can see that there are actually two neighbors that could be candidates. That is a question now we have to decide which one, but in this data set we know that we need to take the first one. Let's say the first one we encounter and see what comes out. This gives us now an additional column in our data frame, and where you can see the distances that we have two positions that have the same distance, and then the rest they increase. And actually there is a couple of other pairs which are the same, but they are further away, so they are not even counting into the nearest neighbor. And now we can see what happens when we look at each point, where we step through the points in the 0 data frame, and see which ones they are closer to in the first in the next frame. So this is essentially just a nice animation of what you saw before, and now we can say that we chose the first occurrence of the nearest neighbor, and we see, yay, everybody are pointing -1, -1. So this looks good. Next frame and the following frames, you can see that it follows the same pattern, and it looks like we have a very consistent -1, -1 motion in this data. There are also other ways to visualize this. If you have a more complex data set, you start looking at visualization techniques like streamlines or something like that to better visualize how the data is moving around, or how the points are moving around in the data. Now to compute the average flow, there is an interest to have at least some kind of average behavior, look at average behavior, and we have 3 ways of doing this: spatially, temporally, and spatiotemporally. And now if you just take the average of what we have, that would be what we see, -1, down here. That is what is calculated for all displacements. What we also can do is start looking at the spatially averaging. First, average in each frame, so you actually reduce the data. In principle, what you're doing is applying a box filter, you could say. Then you get the spatial averaging, or any spatial convolution would give you that. On the other hand, if you go on to the, and then we would get, of course, the -1, -1. And that can look sometimes a little bit strange if you go in. I thought I missed something, or the order has changed. Anyway, if there is some randomness, you can see that there are some numbers here that are flick-flacking around. But anyway, the major changes, they give the flow field in this direction. So it's a -1, -1 flow field. And the temporal averaging, then you start looking between the frames. So then you take the same point in each frame and do averaging across here. It can actually also be helpful to do this because of the noise between the images, particularly when you have low signal to noise ratio. It can actually help also to do some averaging in the time direction. And that is what we can do. And we get, well, this display is one thing I never got that one really good. It's a bit confusing here because of this scale. It should be -1 to -1, but somehow it didn't want to talk to me when I did the preparation. But anyway, it should be a couple of arrows going down. Then we have the combination, the spatial temporal relationship, where we do both averaging in time and in space. And then we can have the more robust averaging system. But of course, that costs a resolution a little bit, because as soon as you do averaging, it's a low-pass filter. So the more transient behavior would be lost if you do it like this. So you have to balance that between what you want to see and how noisy the data is. This is a pretty long one. So here we are stepping through different delta X and delta Y. So you can see that the arrows, they are changing over the time frames. And sometimes the vector is longer and other times it's less long. So you can see that the flow field is changing a little bit over time from frame to frame. So this is also kind of visualization you can do. But of course, it's always tricky to do visualization when you have more than 2 or even more than 3 dimensions. So you have to step down into different methods of showing the features you want to look at. Next thing is a little bit problematic when you go into a longer time series. It's harder to compare. So if we now have a very long series, one that is moving around, a little bit strange movement, so it's jumping up and down and sideways and everything. And this will be a pretty confusing visualization when you do it. And you can see here that we are moving around, and then all of a sudden you can see that there are some points that are coming back to the previous one, which is really confusing. And then it's getting harder and harder to get the right tracks in the data. So that is one thing. And you can also see here when you start doing more complex work, you can see that the nearest neighbor sometimes gets pretty confused, and then we have to think about some way to improve our tracking technique, and then we have to go to different methods. Looking at this flow, you can see that it's moving around. X is going up and down. Y is also going up and down, except for this point where it's going one step extra up. And that also shows in a little bit in the vector graph, which goes down, down, and all of a sudden one goes up. And this is one, and you can see again using this field that sometimes it's always is pointing up or down, and then all of a sudden there is one up and down at the same time. So it can be different flows you can extract from this data. Another thing to think about is it's not, or actually usually the data is never nice. You have signal to noise ratio to play with, you have limited field of view, you can maybe not even see the full depth of field. We have problems with the segmentation. Sometimes we don't segment right things. And then on top of it, as we are talking about time series, you have motion blurring, so you get motion artifacts. It's even possible that if you have this limited field of view, that an object is going outside of the screen and then coming back again. So how you know that this is the same object? Things like that you have to play with, and or actually be able to track and know what's happening. So one thing is the jitter or motion noise that, oh, that one is coming strange. So that you have your motion and then there comes a little jitter, so with some amplitude and some direction, and these are random variables. So you go to a certain point and then from that one it's jiggling around a little bit, and that is the jitter. That is the question of stability in the sample itself, also how well you can acquire the positions. So we have a couple of different limitations on how to track. We have different flow rates, we have flow types, density of things, also how often things appear and disappear. Could be cells dividing into new cells, and you want to track them, and or something else is splitting or merging. So tracking this can be tricky, and you have to have an algorithm that is able to cope with it. Also, again, jitter is also a problem, and one thing that can be annoying when you do the tracking is if the particles are all the same, it's much harder to identify them, identify which one is the one you want to track. So that would be additional information if each individual has a little bit different shape, because then you can use that in the tracking decision. If you were, for example, do the nearest neighbor, you can add the particle shape as a parameter to decide, okay, I have to go this way or that way. So what we can do, first of all, we have to find the limitations to improve our tracking performance. So one side, we can play with the parameters at the acquisition. So how fast we track, how fast we acquire. It's easier to find an object which is close than one that is further away. So if we can increase the frame rate, meaning the travel distance of the items is shorter, makes it easier to find the right one. And also the interference of other particles is less. Of course, we have the resolution as usually. It's easier to determine something if you have sufficient resolution. So that is a natural one. On the other hand, resolution costs time and signal to noise ratio. So you have to balance this. On the other side, we can also play with experiment parameters. Oops. So again, looking at the experiment setup, changing pressures, which gives you a change in flow rate or type. Now, it may be that you want to study a specific flow rate and type, and you can't do much. The dispersity, how unique the particles are, is of course something you could possibly play with. But again, a lot of these parameters that you could possibly play with is maybe even something that you want to maintain in your experiment setup. So it's not easy to change the experimental parameters. But usually it's a balance between what the acquisition can do and, on the other hand, how you can modify the experiment. And that's something usually done during the experiment, that you try to tweak and tune even at the beamline. So you have some different sets of samples, and then you work, you try them in an initial test. So there is a lot of ways you can improve tracking by experiment design. Here is an example that became pretty small, but there was a flow simulation of different flow tracks, and there was an introduced jitter in this of not so much, but well, a little bit at least, going in any direction with a fixed amplitude, and then you can see what the tracking is doing with these, and it seems like the tracking, nearest neighborhood tracking, is doing pretty well. So how can such a simulation help us in the experiment? One thing is we can actually see how far away, how fast we need to sample, and also how big is the jitter and what can it do. And actually also this kind of simulations can be a starting point for if you have not sufficient data for your experiment. You can also use the this in the design of image processing methods, and also validate in what operating range they can work. So we can see from a simulation like this, we can, for example, play with pressure against acquisition time, or see what comes out, and with that we would have nicer parameters in at the experiment time. Also, question is always, what is enough? And it's always difficult to say what is enough, and that has to be told actually from experiment to experiment. So in some cases, you have a little error somewhere, and that can blow up in large errors in the parameter you want to look at. So it's not easy to really see the whole workflow. So here are some examples. 5% error in the bubble position gives more than 20% error in topology of how the process behaves, and that's a pretty extreme thing. Also, 5% error in the shape of volume estimate, that can also be a very damaging to strain tensor calculations later. So it's important to see how the errors are propagating throughout the system before you decide what you need, what kind of resolution or precision you need from the experiment data. So you can always add a lot of alternative or adding up in different ways to the tracking algorithms. You can check if you have 2 points that are essentially the same, well, so you can look actually in the literature, in the book by Goshtabi, you will get a lot of ideas, and some of them are much more advanced than this nearest neighbor or even these two methods. It all depends on what you really need in your experiment. So we can even add some prior information, like we know that something is moving in some certain direction. We can, for example, add in this minimization process, we can add a velocity offset before we start doing the comparison, and that gives us the neighborhood where we should look. We can also adapt it from the previous average movement. We can compute this offset. Of course, you can also do offsets based on a physical model of what you expect, how things move. You can use the track derivative. So you follow what the track looks like and see that, okay, now it should be going up or should be going down. Extreme cases, you can even use Kalman filters, which are stochastic models based on stochastic models and the derivatives of the tracks, and to predict where you should look for the next one. So that's a pretty advanced technique, but has been, in some cases, been shown to be very successful. Well, then the next thing is looking at different tools. Nearest neighbor is a good starting point, simple, easy to understand, but for complicated data sets, you can't use it. So you have to look for other things. For example, multi-hypothesis testing, where you add more information into the tracking. Also looking at multiple paths. Maybe things are splitting and merging. So for that, you need really to have something that is handling that. And in particularly for the merge and split, it can help if you have a physical model, how things are behaving. And with that, I think I make a break, and then we continue in, say, yeah, let's say 10:15. So it's 8 minutes break. I got a question here about Ashtabi, Goshtabi, actually. Yes, I did some modifications on today's lecture since yesterday evening when I uploaded it. So I will upload the slide after the lecture, so you will have the latest information too. So no problem.